多少钱啊？对，3块，多少啊？外面卖只有多少？2块半，差不多。去那里装热水？哦，那个 refill。Hey, good morning to everyone. Let's start our class today. So if you haven't seen your midterm, right, I will take a copy and then send it to you, and then you can check your solution with my solution. If you think I overlook your answer, then you can claim marks from me. Okay. If I forgot to send you your exam copy, please contact me. Okay, so before we start, let's do some pop quiz. What is this? What is 2? 1 plus 1. Okay, 1 plus 1. But sometimes when we write 2, we want to see 2 as a function. So if we see 2 as a function, what is this function? Constant function. So meaning you plug in any x value, I always get 2. Okay. So we define the constant function C from R to R to be a function that send every point to C. Okay. So be careful when you see constant. Okay, whether it's a constant number or a constant function. Okay, constant number or constant function. Okay or not? So for example, in the calculation we did last time, when we show that the constant function have derivative 0, right? So we computed what is fx plus h fx or fy fx. Okay, what are all these? Okay, remember last time we write c minus c, right? C minus c. Okay, is it really c minus c or not? Is it really number minus a number or not? Okay, which one is function? Which one should be function? Which one should be number? Which c should be function? Which c should be number? First one should be a function. Second one should be a number. Okay, so let us circle it. So this one is a constant. This one is a function. Why do you say so? Why do you say so, Jack? Why? Why do you say so? So the first one, this h is a variable, right? For the first y is also a variable, but what is x? This x is a fixed x, right? Is it fixed or not? Then we fix it. You can think of x as any real number, maybe 1, 2, 3, 4, 5, 6, 7, 8, 3.3, 5. Okay, so it's fixed, but h is a variable here. Okay, does it make sense? Okay or not? Okay, so in this case, we will write like this more formally. Okay, instead of writing c for fx plus h, we write cx plus h. So meaning what? This f is a constant function. Okay, but you see, a constant function c minus c, why do you get a zero function? Why? Why? Why a constant function c minus c, you get a zero function? And why? Function 往下移 c. What does it mean by that? You deduct the value of the constant function by c at every point. Then what's the new function? What's the value that the new function gives you? 0. So at every point you get 0 value. So what function is that? Zero function? Make sense or not? Does it make sense? No? Which part doesn't make sense? Which part you don't understand? Sorry? Line 2? This line or this line? This line here? Okay, so why do we write like this? So what is fx? X is a fixed number. Okay, and then this function applied to a fixed number should give you what value? Constant c. Okay. How about this part here? Fx plus h. Constant function on x plus h. Okay, so what? So this part is a constant function. And then the second part is a real constant. Okay, make sense? Okay, now. Okay, and then we want to ask the difference of these two function or constant function here. What does this difference equal to? Is it a new function or not? If it is a new function, what function is that? Okay. 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 So what does this difference give? If you fix an h? 0. If you change h, still 0. Correct or not? Why? Because this is a constant function c. What does constant function c do? You give the constant function any point, the function give you c. So at every point you get c minus c. So what function that do that give you 0 at every point? What function is that? 0 function. So it is equal to the 0 function. Okay, now. So to check two functions are equal, how to check? Remember this. How to check two functions are equal? You need to check at every point. Yeah. So at every point, what is the value you get for the difference? 0. What is the function that always give you 0 at every point? 0 function. Okay, no? Does it make sense? Clear? Okay. Yeah. So this is a better way to write these calculation down. Although maybe in calculus, in your high school, you just put C minus C over H, something like that. Okay. So why I emphasize this? Because you need to really know how we define limit. Okay, we define limit on functions and also on sequence. Okay, we didn't define limits on numbers only. We didn't define like that. If it is a number, what kind of limit you want to look at? The number is not moving. Correct? When we look at limit, because sequence is like going on and on and on, we want to see what happened in the infinity end, right? And function also, we have a lot of points in our domain. We want to look at how the function change. Okay, so we have limit. If it's just a constant number, what is limit 2? What is that? Where 2 have to go? 2 is just 2. No need to go anywhere. You get what I mean? So when you are dealing with infinitely many points, you need limit. Okay, we want to see how is the behavior of the sequence or behavior of the function. Does it make sense? Okay. Okay, so this is about constant. Yeah, this is about constant function. And one more thing about yesterday one. So let's recall what's the local. So let's recall what's the local extrema theorem. Local extremum theorem. By the way, extremum is a singular nouns. Okay, if you want to use plural, is extrema. Okay, if you want to talk about a lot of extremum, it is extrema. Okay? It's like what? What kind of plural also look like this? Maybe stoma and stomata. And then what else? Can't think of it now. Yeah, maybe next time we can share. Yeah, so a bit different, but I think sometimes they also use extremums. Put an S also can. But yeah, extrema is one of the accepted word. Okay, so what is the local extremum theorem doing? Anyone remember? Let F be continuous on a closed interval and differentiable on open interval AB. Okay. Note that what's the difference between these two? I just throw away the endpoint. Okay. Then what? Then if F has a local extremum at C and F is let me see. I think should be differentiable at C. Let me check for sure. Okay, and differentiable at C. Then F prime C is equal to 0. Okay, so really, I think we don't need to differentiable at every point first. Just focus on a single point C. Okay, and has a local extremum then. Then the first derivative there must be 0. Okay. But let's say, is it possible to have a local maximum at C, but it is not differentiable there? Is it possible or not? Can you think of a case? Not differentiable as C, but still has a local extremum there. So this is a bit like our question 1 in exam. Can you construct such example or not? Can. Not differentiable at a point, but still have local maximum or minimum. Can you give one example? So first you need to find one function is not differentiable at that point, and then you need to prove that it is a local maximum or minimum. Is it possible? I give you maybe 2 minutes, talk with your friend. Can or not? Give you 2 to 3 minutes, talk with your friend, discuss whether you can have non-differentiable point, but it is a local maximum or minimum. Yeah, talk with your friends, discuss with your friend. Okay. Sorry, extrema 是什么意思？你讲什么？啊？听不到。Yeah, yeah. Okay, try that. Yes. Yeah. Okay, try that. Okay. Got idea or not? Sorry. Construct an example and then prove it. Okay, so yeah, so Colin said you can use absolute value function. Okay. I think last time we proved that absolute value function is not differentiable at 0. Can you recall why? Limit is different. So what's the limit? What's the difference of the limit? Yes, different limit is different. If you choose 2 sequences that converge to 0, one from left, one from right, what's the limit of the secant function? The fy minus fx over y minus x. Yes, one is 1, one is minus 1, right? Because why? Because exactly you can write this part of function as f1x equals to x, and then the other one as f1x equals to minus x. Okay, so one limit is minus 1, the other limit is 1, the secant. Okay, so doesn't exist at 0 because left and right is different. Okay, the limit of the secant. So it's not differentiable. But where is the local maximum or minimum here? Where is it? At 0. Why? Why? Why 0 is the local maximum or like local minimum? Minimum. So why is it a minimum? What do you need to satisfy to be a minimum? In the domain? For every point. Correct or not? So you can see that for every x in -1 and 1, okay, fx is what? Fx is equal to modulus x. Okay, and then this number should be what? Greater or equal to 0, where 0 is equal to f0. Make sense or not? Does it make sense? Okay or not? Does it make sense? Not okay, just say not okay, because it's fine. We are all starting to learn. Okay. If this one not okay, then later you will stuck more. So you must make this okay first. Everyone follow or not? Okay. No question for this one? Okay. So hence 0 is a local. Okay. In fact, it is a local maximum. It is a minimum actually, right? Because it is true for all points. Okay. Local minimum. Remember what is local mean? You just need to true for some open interval around you. Okay. But this open interval can like increase up to everything inside your closed domain. Almost everything except the endpoint. Or actually, okay. So even if your function is not differentiable, you might be able to find local maximum. Okay, local maximum. But the converse of the local extremum theorem is not true. So what's the converse of the local maximum says? If you take the converse, if the first derivative is 0, then f have to be differentiable there, and local extremum have to happen at that point. Okay, but if you look at the function s cubed, okay, you look at the function s cubed. If you compute the first derivative at 0, what do you get? And what's the first derivative of s cubed? 3x squared. So if you evaluate at 0, what do you get? 0. So maybe you say, hey, here first derivative is 0, and maybe there's a local extrema happening here. But no. Why no? Why no? Why no? So if you go further left, there will be someone less than you. If you go further right, there will be someone greater than you. So you cannot find, they don't exist a r greater than 0 such that this point is a local maxima or minimum. So if you go a bit away from this 0, there will be someone less than you, someone greater than you. Does it make sense? Okay. But you need to show it rigorously, of course. Okay. Does it make sense? At least from the picture, can you guys see it or not? If you go a bit less, you need to go down. You go a bit right, you need to go up. Okay. Does it make sense? Any question or not? Okay, so the converse of a local extrema is not true. Okay, we have an example here. And this local extrema, right? Remember, the C we find is not at the endpoint one. Okay, the C we found is at the open interval of AB. So we don't know about local extrema that happen at the endpoint. So that's why you need to check yourself. Okay, that's why we have these first derivative test says that if f is continuous on the closed interval and then differentiable at the open interval AB, okay, both of them is about AB. One is including endpoint for closed, not including endpoints for open. Then the extrema of f on the closed interval AB can only occur at the endpoints A, B, or any point in the middle of AB, such that this point, the first derivative is 0. Okay, does it make sense? So that's why in calculus 1, they keep asking you to check, okay, go and find the first derivative 0 points, and then check the endpoint values. Need to compare. Okay, so this is the reason. Does it make sense? Okay, you need to check the boundary point yourself. Check the value. Okay or not? Does it make sense or not? Okay. Yeah, question. A plus, where got A plus B? Oh, not A plus B, it's at B. At B. At B. Okay, at B. At A. Okay. Yeah, so that's why this is the problem. That's why we think that latex is good. You know why latex is good? Because now when latex type AT and A in a with money, you know money, you type latex, right? You need to put money, right? To make the symbol change. So the symbol A and the A is different, letter A. So that's why you can differentiate. But now I'm just like writing. So sometimes quite similar. Yeah. Okay. Yeah. And right. Okay. 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 Any question? Any question about this corollary? Any question? No question. Okay. And then yesterday we proved Rolle's theorems and means values theorem. So can you recall what does Rolle's theorem does? Now what does Rolle's theorem does? If the endpoint have the same value f, then you can find some point in the middle that has derivative 0. Okay, so you need to remember, just remember using this diagram here. Okay, you have um, FA equals to FB. Okay, FA equals to FB, and then you can form a straight line because they are the same, right? So you can form a straight line between the two. And then the problem is why every continuous function, okay, between that connects FA and FB has derivative 0. I mean, have a derivative 0 at some point in the middle of A and B. Okay. And so the idea is if you have continuous function on the closed interval, you must have some extreme values. Extreme values theorem says that if you are continuous function on a closed interval, you must achieve maximum and minimum point. And then these maximum and minimum point will give you the first derivative 0 point because it is by the local extrema theorem. Because you have local extrema, then the first derivative is 0. Okay or not? Okay. Okay. So you need to make sense of this picture and then you can get the statement easily. Okay, so what's the condition here? The endpoint have to have the same f value. Okay, same f value. So you can think of it, actually you are moving this line, you are moving this line. Can you find this horizontal line as a tangent line of your graph or not? You see? You all see that? Can see or not? So you want to find the middle point in the middle of AB such that it has the horizontal gradient line. Horizontal gradient line, what's the gradient? 0? First derivative is 0. Okay. Yeah. So the first derivative 0 is referring to the horizontal tangent line. Okay. Make sense? Can everyone see? Okay. So the assertion of this theorem say you must at least find one. You must at least find one. Okay, at least find one. You see, at least find one. So this is the least case you can get. If you see F1 and F3, this is the least you can get. Maybe you can get more. You see, F2 got 2 actually. Okay, so if you can imagine if you have more maximum point in the middle, then definitely you have to go minimum first. Okay or not? Okay. So if you want to achieve more, maybe you need to go down more. You have to work more. So if you want to achieve more, definitely sometimes you have to go down first. only you can go up. Okay. I'm not sure how many of you understand this. Okay. Yeah. All right. So this is life. Okay. So we have a generalization of Rolle's theorem. Okay. We don't restrict our case just to FA equals to FB. We can consider FA and FB differently. Okay. Where we can form this gradient again. FB minus FA over B minus N. What is this value here? What is this value here? What is this value here? So let's draw this graph, right? So we have A, B here. Okay, let's say FA here, and then FB here. Okay, and then maybe we have some continuous function, right? Continuous function around it. So maybe like do it like this. I think a bit ugly. Wait, let's do like this. Okay, and then go down. It cannot do like that. It's not a function. Go. Okay, maybe do this. Right. So what is FA? FA or FB? FB minus FA over B minus A. What's that? What's the gradient about? This gradient, whose gradient is that? FB minus FA. See, yeah? FB minus FA is the difference here in Y direction. And then B minus A is the difference in X. Okay? For the points, for what point? For the points B, FB, and A, FA. So meaning what? This is the gradient of the line that joins, or the secant that join AFA and BFB. Okay? Make sense? Okay, no. So this line is equals to Y equals to FB minus FA over B minus A, and then what? X minus A plus FA. Okay, so this is the gradient of the secant that join AFA and BFB. But what this theorem says, there exists a C, middle point, okay, in the middle of A and B, such that the gradient is also equal to the gradient of this line. Okay, so this means what? Between A and B, okay, if you look at the tangent line at every point, there's one tangent line that has the same gradient. Okay, let's see whether it is true for this case or not. So similarly as Rolle theorems, we can move this line about. Okay, let's see any tangent line have the same gradient or not. Okay, you want to try move my line up or down to find the tangent line, the other tangent line that have the same gradient. You can move up a bit, right? So let's move out a bit. And you can see that at this point, okay, it should have a tangent line that has the same gradient and this as this FB minus FA over B minus A as the gradient. Okay, maybe this is one of the C here. Here, so this is one of the C. Okay, and then is there another C or not? Do you see another C or not? How? Maybe you can move down a bit. Okay, here, right? So this tangent line seems working as well. Okay. So maybe there are two of them in this graph here that have the same gradient. So let me draw like this. Okay. How about I just copy paste. Copy. Structure. Colored it yellow. It yellow. Okay. So maybe can do like this and then do like this. Actually not quite accurate. So let us move this C1. C1 maybe around here. Okay. My line disappear. Okay. Okay. So the first C1 is here, and then C2 is on the other side. Okay. No? Okay. So yeah. So how we construct this proof? Actually, we just look at the difference between Fn and this secant line here. Okay. If you are interested, you can look at the proof again. Okay, we won't go through it now. So the idea of the proof is like what Lohoff said last time, right? So how we use Rolle's theorems here, we somehow rotate. It's not exactly rotating, but the idea is almost like rotating. When we look at the difference between F and and this curve here, okay, yeah. So let me rotate for you. So it's about Rolle's theorems already. Can you see Rolle's theorems here? Can you see Rolle's theorems or not? Rolle's theorem says what? If the two endpoints have the same value, then there exists middle point in AB such that the derivative is 0. It's almost the same. Okay. Yeah. Can see or not? So that's why we call mean value theorem as a generalization of Rolle's theorems. Okay? Generalization. But you see, the function we look at is fx minus the value of the line. You see, if fx minus value of the line, the difference looks like this. It's not a vertical difference, It's not exactly rotating. That's what I want to say. Okay. The difference is like this. Okay or not? Okay. Okay, so let's put this graph back. Okay, any questions so far? So far, any question or not? So far, any question? Any question? Any question? I mean, this kind of thing make me feel like maths is really fun. You see, you can manipulate it. Again, manipulate it, then somehow still correct, or maybe there's some other meaning inside the manipulation. Okay, so 如果你要读数学，你要去玩它，因为你不玩它没有意义，不好玩。对，真的不好玩，也很难读，真的。你去玩它了，你才知道哦，原来是这样子用的，哦，原来有这个意思。你一定要去玩它，你不能只算吧？可能我算数学的时候不是，应该是小学了。小学的时候做很多习题，不知道华小，不知道你们是华小上来的吗？华小的时候，这样做很多加减乘除一直做，一直做，一直加，一直减，一直加，一直减，一直加，一直减，减到后来是什么情况，你知道吗？我看那两个尾数放在一起，我就知道答案是什么，我不用再去这样，你懂什么意思吗？啊，你看到尾数，你就知道应该要放什么在下面。尾数比如说有4跟8在尾巴那边，我要减一个上面有4，下面有8，我应该放什么在上面？6，对吗？呀，说意思说什么呢？有时候如果你不明白，你就要做多， 做了多你肯定会知道，但是要做多少多因人而异啊，所以就说你一定要努力，一定要努力。我有学生像天才一样的，不用做的，我不是讲 Larry 啊，我不是指 Larry，我还有其他班的学生，我一进来教，其实就有这种学生在啊。我教 discrete math 的时候，我教calculus 的时候actually algebra 还好，其实嗯，还有什么啊？呀，就这两科哦，嗯，他们在我班好像也没有什么听课的，玩自己的电脑这样玩。但是你考 quiz 他又会他不只会你知道吗？他还对他还哦。你要知道啊，我的 quiz 不是正常的题目来哦。什么叫不是正常？我自己想的，我自己去挖出来的。所以如果你没有花时间去挖答案，你也是做不出来。如果你不会的话呢，会的话，obviously 就是那个答案罢了哦，因为答案不会变的嘛。所以有这种人存在，有这种人。但是如果我们不是这种人，不要讲你不是，我也不是，那我们就努力一点做了。OK，so that's why 我放很多 reference 在那个 Moodle 那边。OK，很多后面的那些习题，有些 solution manual 也送给你了，所以你要至少去读一读，看一看。OK，抄一抄，可以抄的没有问题，但是只是说你做 assignment 的时候要写你自己的答案这样。抄是一种学习方式，但不是唯一的学习。OK，明白吗？好，因为我 observe 到这间学校的学生他不是不会，你知道吗？他是学习方式出问题，他学习方式出问题，所以你稍微调一下，你放的那些一点的努力就可以 magnify 很大了。懂什么叫 magnify 吗？放大 magnifier 放大镜就可以放大很多了，小努力可以放大很多，很多我看到这里的学生他放很多努力出来的东西就这样吧，什么意思呢？读错了哦，方法错啊。我们是华人嘛，华人有一句话嘛，讲什么？中国人啊，工欲善其事，必先利其器。你气都不利，你要去杀野猪，杀不死的吗？皮那么厚，对不对？你一定要用对方法，明白吗？找方法先，OK 才去做，不然你就是人家讲做白工，你是美国总统做白工，OK 可以吗？明白吗？想一想，如果读不出了，是不是方法用错了？改一下，很快的，你一改对好像那个火车上轨道这样，直接冲了那个火车。你看火车一离轨动都动不了了，明白吗？OK 吗？明白吗？OK，找轨道，轨道很重要，找对轨道你可以冲了。OK all right. So right. Okay. So what should we do next? Let's see what are the application of means value theorem. Okay. So what are the application mean value theorem? So how do we apply it? So for example, let's introduce one definition first. A function f on the domain df is called Lipschitz continuous. Lipschitz continuous. Okay. So what does a Lipschitz continuous does? If okay, so you see this is the terminology. 这是数学的语速了。所以 we introduce continuity, right? Continuous. But now I put a word Lipschitz. Okay. So what does it mean by Lipschitz continuous? So if there exists a constant k such that the absolute value of fy minus fx is less than or equal to k times y minus x for all x and y in df. Okay. And the smallest, so the smallest constant k that satisfies this property, we will call it it's true. We will call it the Lipschitz constant. I think Lipschitz has spelled wrong. So L-I-P, Lipschitz, Lipschitz. Okay, so you think that there's no epsilon delta here? No epsilon, no delta. So is Lipschitz continuous or not? Do you think Lipschitz continuous or not? What is continuity? For every epsilon greater than 0, there exists a delta such that if x minus y absolute value is less than delta, then absolute value of fx minus sy is less than epsilon. Do we have continuity here? So fix an epsilon. Do you have a delta you can pick? What delta can you pick here? Can you pick any delta such that it is continuous? Sorry? Yes, epsilon over k. You can pick epsilon over k. Because if you pick epsilon over k, if y minus x less than epsilon over k, then this fy minus fx is less than equals to k times epsilon over k, which is equals to epsilon. Okay, so meaning what? Lipschitz continuity implies continuity. Okay, so Lipschitz continuity is stronger. Okay, so here position Lipschitz continuity implies continuity. How about uniform continuity? What does uniform continuity say? For every epsilon, there exists a delta. Okay, this one is the same for everything. But if for every x and y within delta, then fy minus fx is less than epsilon. So meaning what? You need to have a delta that works for every x and y. Okay, that's less than delta. The difference of them is less than delta. Do we have that or not? Does the epsilon does the epsilon over k, the delta equals to epsilon over k works for all x and y in the domain or not? Does the epsilon over k works for all the point in the domain or not? I let you think for a minute and then I want to write down the definition so that you know what am I talking about. I think you don't know. What am I talking about? One is continuity, one is uniform continuity. So continuity say for every x in R, be epsilon greater than 0, then there's a delta greater than 0, such that for every y in here. If x minus y is less than delta, then absolute value of x of minus fy less than epsilon. But uniform continuity doesn't care about x. So it directly work with for every x and y in df. If x minus y is less than delta, then fx minus fy is epsilon. Yeah. See, everyone see. Hello, everyone. Calling everyone. Come back to chat group. So what's the difference between these two definitions? For the first one, I fix x first. For the second one, I didn't fix any x and y. Can see the difference? But you see the last line here is the same. Oh, last line is the same. But the problem here is with the x. Okay. So what's the difference of the x in the second line here? See, what's the difference? What's the difference when I put this x into the middle? What's the difference? 有什么差别？我把 x 先定住，跟我把 x 放去后面再定，有什么差别？差别很大哦。来，左刷。The delta we choose. So what happened with the delta we choose? A fixed delta. Yes, a delta for a x. You see, I fix x first, then I exist a delta. Okay, so this delta depend on x, maybe also depend on epsilon. Correct or not? Depend on x and depend on epsilon. But here, this delta depend on what? What is the thing you fix here? You only fix epsilon. So this delta here only depend on epsilon. Okay or not? Does it make sense? Okay 差别很大哦，很大，非常大，会给出不一样的 function 出来。Okay. So, just now the delta you pick, does it depend on x or not? Just now you pick delta to be epsilon over k, right? Does it depend on x or not? Why not? Why not? Obviously, you didn't put x here, but why? Like, why you don't put an x there? Why you don't put an x there? You see, when we check this inequality, right? How do we check this inequality? This inequality is true for all x and y. So if you pick delta to be epsilon over k, then for every x and y in df, if what? If the absolute value of x minus y is less than epsilon over k, then it is also true for all x and y in df such that the absolute value of fy minus fx is less than or equals to k times y minus x. This is what Lipschitz give you. Correct or not? Okay, but you make it less than k times epsilon over k. So it is still true for all xy in df. Everyone see? For question? Or any question? Any question? So meaning what? Meaning actually Lipschitz continuity implies uniform continuity as well. then obviously uniform continuity will imply continuity. Prove it. Okay. Does it make sense? Okay, so Lipschitz continuity is quite strong. It's very strong because this inequality here need to hold true for all xy in the domain. Okay, got question? Any question? Got question? Why delta? What do you mean by 差别? Oh, I mean, in the continuity, right? This delta maybe depend on x, maybe depend on epsilon as well. Remember the example we gave last time? Remember the x squared example we did last time? Oh, bless you. Where's the example we did last time? Where's the uniform continuity example? Wait, let me find the example we have now. Oh, here. See? Remember that last time we want to prove that fx equals to x squared is continuous. What's the delta we pick here? You see, our delta we pick depend on epsilon, depend on x. Still remember what we mentioned last time? Because this x squared, right, when it increases, right, it gets steeper, steeper, and steeper. So if you want to fix an epsilon gap, the delta will become shorter, shorter, and shorter. So it depends on x. When you x move further, the delta have to work smaller. Okay, I give you this picture here. Here. So if you fix the same, epsilon, you see, going further away from 0, your delta become smaller. Can you compare the two delta here, delta 1 and delta 2? Delta 2 is clearly smaller than delta 1. And then x2 is further than x1 from 0. Does it make sense? So this means that delta could depend on the point that you check whether it is continuous or not. Okay, so the delta will depend on which point you check on the function it is continuous. If you go further away, this delta gap will become smaller, smaller, smaller. Although you are looking at the same epsilon gap. Okay, this is the formula we gave, right? So you see, this is the formula we gave. And here, you choose delta epsilon to be the minimum of 1 and this guy here. You see this guy here? You see this guy depend on epsilon, depend on x. Okay. So if it is uniform continuity, you no need to, your formula of delta won't involve x if it is uniform continuous. Okay, there's no x factor inside here if it is uniform continuous. Okay. Yeah. Does it make sense? Okay. All right. Okay, good. So you need to remember this simple example. So this simple example will keep your concept right. Okay, will keep your concept right. Okay, and then before we take a break, right, we need to do some small result and then we'll take a break. Little result here. So, yeah. Okay. Yeah, I wrote the Lipschitz stuff. Okay, I wrote it here. Okay, okay then. So so there's a small result here. Okay, so there's a small result here. Proposition, little result before we take a break. Okay. So there's a proposition says that a function f which is continuous on closed interval AB and differentiable at on open interval AB with the derivative f prime x is less than or equal to k for all x in AB is Lipschitz continuous. So Lipschitz is a guy, so if you are interested, you also can look for him for your project. This Lipschitz. So Lipschitz on AB with Lipschitz constant no greater than okay. Right. So what does this mean here? So it says that if I can bound, if I can bound my f prime x by k, okay, then I can prove this. I can prove this inequality here. Okay, so let's remove. We remove. No, like the smaller. Like the smaller. Okay. So meaning if you can bound, okay, bound your first derivative at every point in the interval, then you can prove this inequality here. Okay, you can prove this inequality here. So what to do? To do. You see, these first two lines sound very familiar. These two conditions here sound very familiar. These two conditions. What is this? It's this. So you have continuous function on a closed interval and then differentiable on an open interval. Then what do you have? You have the mean, is it? Continuous at closed interval, differentiable on the open interval. Okay, both of them is having endpoints at AB. Then there will exist a middle point such that f prime c equals to fb minus fa over b minus a. Okay, so you will have this. Okay, no? Okay. So how are we gonna use this to prove that? Okay. So what did we do here? This is the difference of y over a difference of x equal to some derivative. Okay. But in the continuity, what do you have? Difference of y, difference of x. But the question tells you something about the derivative. So the question tells you something about the derivative. Where's the question? Is it? The question tells you how to bound the derivative. Okay, so can you try and put this idea together or not? Okay, maybe we take a break and then we will resume discussing this. Okay, so let's take a break until 10:11. Yeah. 现在。
我在读的时候，
哦，OK，
在读
yeah，
看这是
看到噻。哦，它是那个，
我读不懂
它是拿0到1，
0到1，
然后把中间的1/3切掉，所以是说1/3到3/2切掉，所以你剩2段了。然后你再从0到1/3的1/3的中间那个去掉，所以是呃1/9到9/2那边切掉。
对
啊，
我懂
啊，Yeah，and then 你就一直切，一直这样切，就是01，然后你把中间 remove 掉，给你剩下1/3，2/3， and then you remove 中间的给，这样，and then 你就再去他们中间的1/3，再去掉，
可以这样吗？
切了，然后你拿他们的 intersection 剩下的东西，所以这些 endpoint 会被剩下来，then you 剩一 whole bunch of point。
它只是一种 method of construction 啊。
它是一个 convection，yes。Yeah，
OK，让我再想一下。
yeah。I mean，这个 set 有很多 special 的 property 啊。
哦，
Yeah，可以 try 看有没有什么 continuous function 还是不 continuous function define 在这个 set 上面之间。
Alright。
Hello, testing. Okay, let's start before we end the class. Okay, so actually, what do you want to prove here? Yeah? So let's bring the Lipschitz continuity function, the property down. So let's this. Okay, obviously, this k can be negative or not. Cannot, right? So actually this implies that this k should be a positive k. But let's bring this down. Okay, so we want to find. So this is what we want to find. That is the k, such that that is true. Okay. So any idea or not? Any idea? So first, what do? You fix, since you want to show it for all xy, right? You need to find a k for all xy. Okay. Then what do you need to do? You need to check at any xy, right? Check at any xy. But without loss of generality, we can assume that x is less than y. Do you know what does it mean by without loss of generality here? Yeah, if y greater than x, then I call the yx, call the xy. It's a similar. Okay, yeah, without loss of generality. Okay. And what can we do here? Not that. Where is xy? It's in the interval of AB. Okay. So what? So we can apply means values theorem on the interval, closed interval xy, because closed interval xy should be living in closed interval A. Make sense? Or question? Or question? So meaning it is differentiable at xy and also continuous there also. So by means values theorems, there exists a C in the open interval xy such that what? F prime C equals to Fy minus Fx over y minus x. Okay, now can I? But what do we need for continuity? We need absolute value, right? So we can really put absolute value on both sides. Right or not? Is that true? You have two numbers that is the same, then their absolute value should be the same, right? Okay. Right or not? 2 equals to 2. Absolute value of 2 also equals to absolute value of 2. Okay. Then can you try and rearrange this or not? Fy minus Fx absolute value is equals to F prime C times y minus x. But what is F prime C in this question? Always less than or equals to k, no matter where you pick your x C in AB. So this is less than equals to k times absolute value of y minus x. So you get the Lipschitz continuity here. So it's the same k that bounds your derivative. Okay? It's the same k that bounds your derivative. Clear? Is it clear? Question?
Choose the constant.
Let me think. You can do that, but I think in this context, it doesn't matter. In this context, yeah, I mean, sure, you need to choose k, and then you need to check for all these, but my claim is because this k is special, this k works for every point. If this k depends on points, then you will have trouble. Yeah, but yeah, I mean, you are right. You can choose. So choose k such that absolute value of f prime x less than equal to k for x. Yeah. Okay, no. Okay, so the point is the k that we get here is the k that bound the derivative, first derivative. Okay. Mm. So I mean, yeah, this is a bit like working backward, no? So we want to check when is this true. So this is true when you choose k to be the bound for your derivative. Okay. Any question? Any question? Any question? No? Okay. Okay, so this is done. Okay, so let's do another application. So let's apply to constancy. Okay, so what does this constancy says? Corollary function on AB or continuous on AB with f prime x equals 0 for every point AB is constant. So you see, most of the proposition that our theorem that we look at, almost we have a continuous function because we want to talk about differentiability. So differentiability implies continuous. So continuous function will keep on appearing. And then what does this sentence say? If you are continuous on AB, you may imagine you have some line joining FA and FB. And then at each point in the midpoint, right, you have first derivative is 0. What does it mean? What's the gradient? What's the tangent line at each point? Is the horizontal line. Then your function is really just constant, a horizontal line again. Okay. You see why? I mean, seems like quite trivial, right? Quite trivial, but you see, the f prime x equals 0. I didn't require it happen at the end point. I just required it happen at the middle point. Okay, but it's enough. It's enough. Enough to say that it's constant on AB. Okay. So how should we prove this? How should we prove this? Any idea? How do you show a function is constant? This is the problem. If you don't know, then you cannot show. So what's the how to show something is a constant function? How do you describe a constant function? How do you describe a constant function? The value didn't change, right? So what does it mean by value didn't change? How to check that? Uh-huh. So in other words, you want to show that for every xy in AB, FA equals to, sorry, fx equals to fy. So this is what you want to get it. So how to get this? If you know that f prime x is 0. So how to relate derivative to the change in y? Mean value theorem again. Or you can use the Lipschitz constant stuff, right? Okay. Because it is continuous at AB, I told you f prime x is 0 at every point AB means what? Also differentiable. Not only differentiable, I tell you what is the derivative is 0. So we can apply these theorems here. So what's the Lipschitz constant then? What's the Lipschitz constant here? In the case 0, right? So we just apply this proposition with k equal to 0. We know that f prime x is exactly 0 at all points. Okay or not? Okay. So meaning what? Meaning here we can get fy minus fx. The absolute value is equals to 0. which means fy minus fx is just 0. Okay, now. Okay, so let me write here. We can apply previous proposition with k equals to 0, such that absolute value of fx minus fy is equal to 0, which means fx minus fy is equal to 0. That is fx equals to f1. Okay. Okay. So that's why in your high school they ask you to check whether this derivative is 0 or not. You see, they only ask you to check the inner point. You know what happened? What could happen with this theorem? What kind of example could happen with this theorem here? So let me draw to you. Maybe we got A here and a B here, right? And then you have a bunch of tangent line. Okay, inside AB, the derivative is 0, correct or not? At every point in AB. But this theorem says that actually all this tangent line have to assemble. They have to assemble to a constant point, to a constant line. Okay or not? Does it make sense? Okay. But other than AB, it could happen different stuff. It could happen different things. Okay, other than AB, it could be different. Does it make sense? Does it make sense? So the theorems just tells you every point in the AB, the tangent line is horizontal. Okay, but you prove that this function actually is constant. So these tangent line have to assemble together. This is what this theorem tells you. Okay, no? Okay, so remember, horizontal tangent line doesn't tell you a constant function, but it is implied. You need to prove it. Okay? Because horizontal line could be happen at different level, right? But in fact, they have to happen at the same level. Okay, no? Okay. Okay. So this is about constancy. Let me see. So there's another corollary. There's another corollary. So I think it's an easy corollary here. So if let f and g be continuous on AB and differentiable on AB as well, but no, remember the same setting happens here. So we only require continuity on the closed interval and differentiability on the open interval. Okay, we throw away the endpoint when we consider differentiability. If f prime x equals to g prime x, okay, for all x in AB without the endpoint, then what? Then fx and gx is just differ by a constant. It's just differ by a constant. Okay, for all x. And then for some constancy. Okay, so this is a corollary. How to follow from the previous theorem? You just consider f prime x, the function h, to be f minus g. So you can consider. So you can consider h to be f minus g. And then f prime x is f prime x minus g prime x. They are equal, so this is 0. So by the previous theorem tells you what? H is a constant function. So f minus g is a constant function. So they differ by a constant. Okay? Okay, okay, so this is a corollary. I think these are quite good, how to say, quite good tools, okay, to use in analysis, okay, because from derivative, it can tell you how the function looks like, okay. This is about constancy. Okay, actually we have more application. We have application on monotonicity, right? I mean, how to check a function is strictly increasing or decreasing? How many ways to check a function is decreasing, decreasing? Increasing, decreasing. In calculus, I mean. Yes, first derivative. If first derivative, what? Okay. Like this, like, give me an calculus 1 question. Like, prove what? Prove that s cubed is increasing, maybe. Okay, let's prove this. So how to prove? So you do first derivative. Okay, so first derivative, so not that f prime x is what? Equals to 2x squared, 3x squared. And then, so it's increasing where? It's not increasing on the whole real line, right? It's just increasing on positive r. Okay, so how to show that? Not that the first derivative of x is 3x squared, then for all points in positive r, f prime x is what? Is always greater or equal to 0. Then what? Then what? Can do anything or not? Calculus 1 or how to check function is increasing. What happened here? What happened? You need to tell me can work or cannot work, right? I cannot work, also need to tell me why I cannot work. Huh? Can work or cannot work? Why work? What's the statement you have? Greater than 0. Need to strictly greater or equal? Okay. Need to strictly greater, right? Need to strictly greater. So how to deal with the point of 0? Eh? So, I mean, we can see that so what do we want to say about this? So really, really what? We can see that f prime x is strictly greater than 0 for x in the open interval from 0 to infinity. This is what you have. Okay. Actually, this is enough to deduce it is increasing. This is enough. Hence, f is increasing for x starting from 0 to to infinity. Actually is enough. Okay, actually is enough to just strictly greater than 0 at the point not including the endpoint. You can deduce this. Okay, we will prove this actually. We will prove it. Okay, we will prove it. Yes. It's increasing everywhere now. Yeah, I guess so. Huh? Yeah, it should be increasing everywhere. But let's fix it positive 0. Okay, I want to let you see the difference of the endpoint. Okay, actually, you can deduce increasing from starting from 0 to infinity. Okay, by just checking the first derivative that doesn't include 0. Okay, is enough. We will prove it. Okay, we will prove this statement. Okay, so I mean, let's recall what time is it? Okay, we still have. So let's recall what are increasing function, non-increasing, decreasing, and non-increasing. Let's recall. So what are these definitions? Well, let's given a function on the domain df. Okay. And then first is increasing. Okay, what is increasing? If fy strictly greater than fx. Okay. If for whenever y greater than x. Okay, so sometimes we will say that this is strictly increasing, but they refer to the same thing. Okay, and this is differ from non-decreasing. Where non-decreasing, you allow fy greater or equal to fx. Okay, whenever y greater than x. How about decreasing? So decreasing is the other way around. Fy have to be less than fx. Okay, whenever y greater than x. Similarly, non-increasing if fy is less than or equal to fx whenever y greater than x. So how you imagine this function? I still remember or not? Still remember how to imagine this function? How you remember this function? I mean, how you remember the difference between these? So if it is increasing, right, you can think of it as a slanted staircase. Okay. So this one is more what? More suitable for the OKU person to walk, right? You can pull the wheelchair up. But for non-decreasing, is the one that you walk to A5, or you need to walk up the staircase. Okay, maybe not strictly vertical. This is not a function, right? So maybe we can make it slightly like this. So maybe you go up, increasing, okay, and then you stay constant, increasing, stay constant, increasing, stay constant. Okay, yeah. All right, so this is the difference between increasing and non-decreasing. All right, so what's the theorems here? So let's put down the theorems here. Prove what you guys use in your calculus 1. So suppose, again, f continuous at AB and differentiable at AB also, but without the endpoint. Sometimes I call it a boundary point because when you go higher max, we will call the endpoint boundary points here in this case. Then what? Then f is increasing, okay, increasing on AB if f prime x is strictly greater than 0. Okay, this is what you know since your high school. Okay, and then you also can prove that f is non-decreasing on AB if the first derivative is what? You want to guess? Greater or equal? Because remember, just now we got the staircase, right? Can stay constant a bit and then go up, stay constant. When you stay constant, that's the part where you get zero derivative. Okay, so we have to prove that. Although we observe that, but we still need to prove that. Okay, and is anything else we need to say? So actually, the last thing here is kind of equivalent. So if f is non-decreasing, then you can also prove that f prime x strictly greater or equal to 0. So for the non-increasing or decreasing part, there's an if and only if statement. Okay, so you can replace increasing with decreasing, non-decreasing with non-increasing, and then swap the inequality. You can prove the same result. Okay, so let's prove this result first. Okay, let's prove this result. So let me remark here that, so remark, so similar result, similar results, whole results, whole or decreasing instead of increasing. Do you know what does it mean by this remark here? So you can replace the first statement by the increasing by decreasing. Then you need to change the condition on the first derivative to less than 0. Okay. If you change non-decreasing to non-increasing, then you change the first derivative condition to less than or equal to 0. Okay. So let's prove them first. Or let's prove it. Okay, let's prove it. So how are we gonna prove it? Prove. Okay, how are we gonna prove it? So assume. So let's prove the first one. So assume. So this is the first one, second one, third one. So for the first one, assume f prime x greater than 0. Okay, for all x in AB. And then what do we want to show? We want to show that f is increasing. To show that f is increasing. So to show that f is increasing, what do you need to show? For every x less than y in AB, I'm a bit lazy. This is a shorthand notation. Don't follow me. Can or not? You understand what I say here? Can Actually, this one is a shorthand notation for every x, y in AB such that x less than y. Okay, let's skip this. Okay, so every x and y less than v in AB, what do we have? We need to show that fx is less than fy. Okay, can or not? When you go increase in x, your f also increase. Yeah. So we need to do this. So how to do this? We got condition on f prime x. We want to find the difference in fx and fy. How to do this? Hey, mean value theorem again. So where do you apply mean value theorem? Apply mean value theorems on the closed interval xy. So meaning what? We actually need to fix our xy first. We need to like how to say? We need to We need to check for all xy, right? So we need to fix x less than y first. Okay. And then we can apply mean value theorem on this. Because if y less than x, the interval doesn't make sense. It's empty. Okay, you cannot be greater than something larger. You cannot be greater than something less than you. Yeah. Correct or not? I mean, correct, right? Like if I put like this, can you be greater than 2 less than 1 or not? Cannot. Empty. So this is an empty set. Okay, nothing there. Okay, so we apply MVT on XY. So what does this MVT tell us? Fy, okay, right. There exists a C in closed interval XY such that Fy minus Fx over y minus x is equal to F prime C. Is this enough or not? What do we know about F prime C? Always greater than 0. Which means this one is by assumption. So which means what? Which means Fy minus Fc is always greater than 0. And then this means Fy is strictly greater than Fx. Okay? Yeah. So if you don't have this NVT to tell calculus people, a bit hard to prove. Maybe you can use graph to draw to them, but so this is the analysis way to prove it. Okay, you need the MVT. Okay, you need the MVT. Yes, question. Yeah.
Lower string x less than y. I so both is
What do you mean?
because if the quotient has been larger than 0, then either both positive or negative, both larger than 0 or both less than 0, and then is positive.
You mean maybe one of them is positive, one of them is negative.
For the for Fy minus Fx over y minus x larger than 0. So either both has to be larger than 0 or both less than 0.
Yeah, say again. So your Fy.
If this whole thing is larger than 0,
yeah.
So either both positive or both.
Oh. Why you not just both case, right? You can have let me think. Let me think. Oh, you mean x? You mean x is always greater than y is always greater than x, right? Here, right? So this part is always greater than 0. If you don't restrict, you can consider both case definitely, but for increasing, we just need to check for x less than y. For increasing, we just need to check for x less than. If not, then maybe you need to do different stuff. Yeah. So if y less than x, then this part is negative. If this part is negative, then you might swap the inequality here. Okay or not? Okay. So I mean, so this part here is since y minus x is greater than 0. Yeah. I think this is a very good point to see. Okay, so for part 2 is similar. For part 2, you can see that it's similar. Okay, if f prime x is greater or equal to 0, then this part here is just f prime c is strictly greater or equal to 0. And then in the end, you will get all the greater or equal sign. Okay, this is part 2. Does it make sense? Part 2 is the same calculation with the different condition on derivative here by replacing strictly greater to greater or equal to. Greater or equal to, greater or equal to. Okay, so part 2. replace proof of 1 or replace f prime c greater than 0 in the proof of 1 by f prime c greater or equal to 0. Okay, so that fy is greater or equal to fx. Okay. Okay, how about the other direction? The other direction a bit tricky. This direction. If you know that your f is non-decreasing, then your derivative have to be greater or equal to 0. Okay, this part a bit tricky. So how to show it? What's your goal here? What's your goal here? You want to show that f prime x is greater or equal to 0 for all x in A, B. So what does this mean? So this f prime x is what? Is the limit of what? Limit of f. Let's say we use the x plus h property, the equivalent definition. This limit here have to be greater or equal to 0. Okay, you need to show that this limit here have to be greater. So how? How? You want to show that this limit have to be greater or equal to 0. Any idea? 2 minutes we have to run. But we have to show that this limit here is greater or equal to 0. Non-decreasing, so I mean non-decreasing only work for what? Only for x less than y. We know that. So meaning how to put this there? So for h greater than 0, we know that fx plus h minus fx is greater or equal to 0. Only for h greater than 0. But you see the limit here, random f, as long as converge to 0. So can you deduce random f from this particular case or not? So yeah. Can you deduce this general case from random case or not random case, specific case or not? Ah, 什么 what 对 yes that's true. 小狗 don't know. 什么意思 What do you mean? then what? 这个为什么？有没 x plus h 一定会小过 x x plus h 对，没有错 x plus h 会小过 x，所以 x plus h 会小过 x and then implies that fx plus h. Okay, can sure, yeah, sure, and then over h 的话是大过等于0。
哦，对对对对。
Okay, sure. So sure. Okay, so let me write down what did you say. So we have the top one implies that fx plus h minus fx over h is greater or equal to 0, correct or not? Because h is positive. But at the bottom, what happened? You are dividing by negative h. So you will have the inequality swap, correct or not? Because you divide. Okay, so meaning what? If you take left and right limit, both of them have to be greater or equals to 0. Okay, but what? But it is differentiable. So last time the theorem says what? If it is differentiable, this limit here have to be equals to the left and the right limit. So the left and the right limit both greater or equal to 0. So the original limit also have to be greater or equals to 0. Three of them have to give the same number. Okay or not? Okay. Okay. So by since f is differentiable at x, so the left limit and the right limit, so the left limit and the right limits have to be equals to the original limit. So this is to be equals to the original limit. So 0 plus and equals to the limit from 0 minus, but both of them is greater or equals to 0. Okay or not? Okay. Okay. Yeah. So if both of them 0, then the original one have to be 0. If both of them is something straightly greater than 0, then the original one also have to be straightly greater than 0. Okay. So three of them have to be the same if it is differentiable. Okay. Any question before we finish up? So the next class, we will finish up derivative. We will prove generalized means values theorem, and then prove the L'Hopital rules. Why you can use L'Hopital rules? Why the point 0 over 0, infinity over infinity, you can differentiate, and then take limit. Okay, we'll prove that. Okay, any question before we dismiss? Oh, okay, so see you next week.